I'm going to give you a brief introduction to talk a little bit about the remit of the Climate Change Task Force, and then a little bit about the work plan that we have. And then predominantly that relates to two set of explainers that have now been published on the website. And we will have David Stephenson go through the first climate change explainer, and the second one will be done by Dario around extreme events. And then we'll move on to audience feedback and panel discussion. So just some context around the Climate Change Task Force. So this was something that I started when I became RSS president, and I felt it was one area that we weren't really strong enough in terms of having a voice. So we were coming out of COVID, we had a very strong voice around COVID and medical statistics, very strong voice around official statistics, but climate change seems to be one of those areas where statisticians weren't as involved as perhaps they should be at the RSS. And so we've been looking a little bit around what can we bring that's unique from statisticians to the climate change debate, not wanting to stand on the toes of climate scientists, but feeling that there's some unique aspects that the RSS can bring to the discussion. And that sort of led a little bit to the explainers. So the remit, and we've predominantly focused on increasing the public understanding of statistical issues linked to climate change. And when Dario and David will talk a little bit more about these things, the idea behind the explainers is to focus on the statistical aspects of explaining why some things happen. So explain why we have a 1.5 degree target, etc., and what the baseline is, etc., and then why something like a change in the global mean will lead to a disproportionate increase in extreme events. So we're trying to come up with areas that are very statistical without actually just trying to explain the science per se. So it's trying to get a unique take on it. And we've had a little bit of debate as we've gone through about how statistical these explainers should be. And there's a bit of tension, I would say, about, do we go too statistical or not statistical enough? So again, we'd be interested to get your feedback on these things. So the first focus, as I say, on that remit is about public understanding, and that's where we put a lot of time at the moment. The second one is supporting the production and communication of evidence-based analyses. The third one is emphasize the importance of fundamental statistical principles and best statistical practices in relation to the analysis of related data. Something we haven't looked at yet, which is contribute to the design of future data collection. And then this is probably a big area. Consider the statistics of the wider impact of climate change on areas such as health, economics, migration. And that almost covers almost anything, because climate change can have a big impact. But one of the nice things about the RSS is we have a medical section group, we have an official statistics section, etc. So we have a lot of expertise that can go into these other areas, and we need to try and work out how far we're going to sort of spread our tentacles into those areas. But certainly the difference between the effects of climate change versus how do you mitigate the effects of climate change and the broader impact. And we'll talk a little bit about later on some of the explainers. We also think about accounting for the differences between the individuals, the government, and corporate levels. So how we might explain things or the impact on certain groups and what they can do to have an impact is sort of divided into individuals, government, and corporate as well. We're also looking to, in terms of having a stronger voice, we're looking to work with the Science Media Center. So the Science Media Center is something that essentially distributes articles essentially for comment to the wider scientific community. And the RSS has a very good reputation, particularly around COVID, for commenting on those things that come out. And we're trying to really get a stronger voice in terms of climate change, so the RSS is going to be one of those places that people would immediately come to and ask for comment. So we're trying to coordinate our responses on climate change and net zero, and on calls for evidence, etc. And then finally, an interesting one is where appropriate work with adjacent organizations. And we've been having interesting conversations with the ASA with their climate change group. I was over at JSM a few weeks ago and got invited to one of their meetings. And we're looking to see whether we can work together on the explainers and are there other areas we can work together on to influence? So we sort of, strength comes in numbers. We're also looking at working with the ISI. ISI certainly work a lot with developing countries, and that's another area where we feel we can have some influence and maybe produce some useful outputs together with the ISI. So this is sort of that working with other groups, that sort of collegial approach. And David might mention a little bit later, we are having some talks with the Royal Meteorological Society about education and about using and developing some outputs that we can use within schools that have some statistical aspects of climate change in them. So that is the remit of the organization. These are the members, and RSS, of course, is an international society. So we have people from, actually at the bottom there, we have Jason West from Australia. We have Aidan Rafferty, who's based in the US. So we have quite a nice mix of people. We have Paul Allen from Official Statistics as well, and Paul is here today. So we have a mixture of people from government, climate, sort of people working in climate change. It's chaired by or co-chaired by myself and David Stephenson. And David is going to be speaking a little bit later. So we have quite a nice group of active members who are working on these explainers. So what we're looking to do today is to go through and explain a little bit about what we've been doing in these two areas. Both these explainers are going to be published in Significance. So they are currently on the RSS website. They've been distributed out on social media. And we're looking for ideas as well as how we can get that information further out there. They've actually been translated into Italian, would you believe, which is very exciting. So we're trying to work out how to get those explainers further out. And then to talk a little bit about the explainers we're looking to work on at the moment. So we have 3 active explainers. One is around attribution. The second one is about uncertainty. And of course, for the RSS, that is a very broad topic, uncertainty. And some of the things that David will talk about is around uncertainty as well. But we think of a specific explainer on uncertainty. And then we're progressing one at the moment through Paul Allen and the team around access to government data on climate change. So they are the explainers. And just before we get into that, just in terms of slide sequence, when we finish that discussion, what we'd like to do is to have the people here, and maybe if you can, I don't know how far you are from each other, but just sort of have a chat for maybe 5 minutes or so on the work that's been done so far and to get your ideas. And then we'd like to come back and have a bit of an interaction with the people here to talk about what other explainers do you think would be good that we should do? What are the other priorities for the Climate Change Task Force? What can the RSS bring to the table that is unique? And we often do this in a lot of areas. I mean, the AI Task Force is doing exactly the same thing. What can we bring that's not duplicating what other people are doing, but sort of brings a unique sort of voice? So, example, with the AI Task Force, we're looking at things like the practitioner's view. We have a lot of practitioners who are not in big tech and not in academia, but actually working on the coalface. So that's a unique view that we have. And then around inputs into AI, we feel there's not enough time spent on inputs into AI. So this is a sort of unique view. So what we're trying to get here with the Climate Change Task Force is get your input on what are the unique things that the RSS can bring to the table that don't duplicate what other people are doing. Okay, so with that, I'm going to hand over to David, who's going to talk about the first explainer.
Great. Okay, thank you. Yeah, well, I'm going to try in this bit to go through our first set of explainers that were on the 1.5 degree target. We think the 1.5 degree warming target, people are talking about that a lot these days. We thought that was a good one to try and explain a bit. I'm going to try and do in this few minutes, I'll do like the last speaker this morning said about the 3 C's, so hopefully we will stay calm. I'll give you some context and hopefully you'll have some curiosity after I've shown you some of these things. You can get angry about the results later. You can think about your emotions when you see some of the things. I mean, people do react. Climate anxiety is becoming more of a thing, so it's okay to acknowledge that. Probably to set off your climate anxiety, here's an example of what happened. This was on like last day of May this year in Delhi. temperatures got up to between 45 and 49 degrees Celsius. That's the temperature, it's measured in the shade. So that's air temperature in the shade. So you imagine being in air temperature, the coolest you can get is 49 degrees. It gets warmer if you go out in the sun, right? So that is hot. And people here were trying to keep cool by spraying water onto the tuk-tuk drivers. The people here were not getting cool, were having to go through this. So, and people were being exposed to these very high temperatures. So, and we're going to see a lot more of that in the future. So that's what we're going to try and explain. And Dario will show you more about the extremes. The first two explainers we did, the first one, well, we did explainers on the 1.5 degree global mean warming target. And I'll go through those in the slides. Dario's going to go through the explainers we did on extreme weather. And we used Heathrow Airport as an example for that. It's not as hot as Delhi, but it still has a lot of people living near it who can feel the heat. And these explainers are up on the RSS website to look at. So back in 2015, there was a meeting of the United Nations at the climate conference, COP21, in Paris, and 195 nations of the world actually signed up to the Paris Agreement. Not every nation signed up to it, but 195 did. And they agreed to try and do something to limit the amount of warming. And this was the first legally binding international agreement to try and do something about limiting the warming on the planet. And the Article 2.1a of what they drafted said they'd try and hold the increase in the global average temperature to well below 2 degrees above pre-industrial levels. And they will pursue efforts to limit the temperature increase to 1.5 degrees above pre-industrial levels, recognizing that this would significantly reduce the risks and impacts of climate change. So people misuse the word. It's not a target. We're not trying to hit 1.5 degrees. We're trying to avoid it. It's not a threshold. People use the word threshold, which is a bit dangerous because it's not like something terrible will suddenly happen at 1.5. Things are just getting progressively harder as it gets warmer, yeah? And they get more so. So it's the idea is to try and limit it. 1.5 is a bit like the car is running off the road. 1.5, you're going past the pavement. 2 degrees, you've gone off the edge of the road completely. So the idea of 1.5 was to try and make sure you do avoid going past 2. Yeah, that was the general philosophy. There's nothing magical about the number 1.5 or 2, but, you know, basically it's decided that above 2 degrees, we don't really know what's going to start happening in the climate system. Sort of some fairly unpleasant positive feedbacks could happen, tipping points could start happening. So we really don't want to push the planet above more than 2 degrees of warming. So the question is, the first question in our explainers is, how is the 1.5 degree global mean warming target defined? And unfortunately, in 2015 in Paris, they didn't actually come up with a definition of it. So they wrote the legal document, but they didn't say how this target would actually be defined. And climate scientists are still grappling with this. There's a paper that's being written at the moment, actually, by climate scientists about how on earth do we define this 1.5 degree target? It's not uniquely defined, yeah? And there are various ways to try and do it. So I'll go for it. The first thing you do is you take global mean temperature. So that's the first problem. How do you estimate that? So you take all the available observations in the past of air temperatures, surface air temperatures over land. You take sea surface temperatures over the oceans. You try and do things over sea ice, which is tricky. You try and get all this measurement data for every day in the past, and you then average it over space, and you average it over time to try and get a global average. That's already a massive process, and it's quite a difficult process to do, which climate scientists have been doing for quite a while now. If you can do that, you can sometimes get monthly mean temperatures, and if you look on this curve here, this is the year from 1850 to 2050. The grey line is the monthly mean global mean temperature. Yeah. So you see them sort of bobbing up and down. There were some low ones here in the end of the 19th century, and then the grey lines here are starting to go up, as you can see. you want to do the temperatures relative to pre-industrial. That wasn't defined really in Paris, so there's different choices, but one choice that is common is to choose the period 1850 to 1900, and then subtract the mean for that period from the global mean temperature. So these grey lines here are all, the average over the 1850 to 1900 period is 0 by definition. So these are relative to that baseline. And you can change that baseline. People do try different baselines. This idea is basically this bit wasn't affected too much by humans, and then this bit now is starting to be affected by humans. So this is our pre-industrial baseline. The final bit you have to do is you're not interested in the variations from month to month or year to year. You're interested in getting the trend. And so then there's the question of how do you estimate the trend? And on here I've got a trend estimate which I did using a generalized additive model, a spline model. There are various ways, but basically you have to average over time, or you have to do some sort of method to try and smooth out the data. This is my generalized additive model with an autoregressive residuals. So what you can see is it basically went along, went up a bit here. You might say, well, why didn't it carry going up in the mid-1950s? It sort of flattened out. That's due to aerosols. That's sulfate aerosols in the atmosphere, so we were producing a lot of air pollution at that time, and that led to a slowdown of the warming. Things got cleaned up a bit. People stopped emitting as much aerosol in the northern hemisphere, and then since about the 1960s, it's been up and up and up and then going up. And that's the red line. If you follow it through there, it's going up at about 0.23 degrees per decade. It's currently at about 1.3, so we've got about a decade left by my calculation before it hits 1.5. Obviously, humans could do something and reduce carbon emissions, and you could flatten that curve out. Let's hope that starts to happen. But, you know, it does depend on human behavior, what will happen to that line in the future. So that's the procedure for defining it, and we explain that that's written down in the explainers. I also produce this plot every month, and that's available on the link, so you can click on it, and you can get the data if you want, so you can have a see how I got that. Obviously, so that's the basic idea of, so to get the target, you need to work out the global mean temperature, estimate that. You need to somehow work out an anomaly from something in the pre-industrial past, and then you have to somehow estimate a trend. So it's quite a procedure, and there's quite a lot of debate about the different procedures. Next question was, what are the main sources of uncertainty in knowing when this target will be exceeded? Because it's uncertain, yeah? And there are lots of uncertainties. First uncertainty, the observations are imperfect and incomplete. There's not a weather station everywhere on the planet, especially if you're over the polar regions, over Arctic sea ice, there are not weather stations measuring air temperature. Yeah? So the observations are incomplete, and they varied over time as well. Over populated land areas, it's slightly better, but over unpopulated areas of the world and over the seas and things, it's not easy. So there's incomplete observations, and also the measurements are not perfect. That raises the question also, you've got a set of observations scattered across the planet. How do you then make a global average? That involves a sort of interpolation problem, extrapolation problem, spatial extrapolation problem across the planet, and there are various ways to do that. So that's another choice that comes into it. How do you choose the industrial baseline? What do you consider to be the before human influence? Which trend method do you use? So all these things will affect your estimate. Natural variations. In the future, various things can happen. The climate system varies. There can be El Nino events, like there has been in the last year. There can be a volcanic eruption. Tomorrow, a big volcano could go bang on the planet, and it will cool the thing temporarily. That lasts for a few years. There's various things. Solar emissions, solar radiation varies over time. So there are variations in all these things that are natural, and that will change the estimates. And the other bit we don't know about is we don't know what the future emissions are going to be, because that depends on human nature and politicians and society, how we're going to change our carbon emissions. So they can all change it, and they can change this sort of estimate. So roughly, a lot of those things add up to about 0.2 degrees, roughly about 0.2 degrees uncertainty. I would say a standard deviation of about that. So you could definitely move that red line around quite by 0.2 degrees, which equates to about a 5-year change in when you think it's going to pass the 1.5 degree target. So it's quite hard saying, to actually say, have we gone past the 1.5 limit? It's going to be quite a tricky question. There'll be quite a lot of debate in the literature when some people think we already have, and some people think we haven't. So it's going to be interesting, the debate of, have we gone past the 1.5 limit? So we're not even sure if we have, so, because of the uncertainty. The third question we had are, what are the local implications of reaching the target? The danger with the global mean temperature is that you don't actually, that's not the temperature you warm up at locally. The warming, if you look at the warming on the planet from the climate models, and from historical as well, is concentrated in certain areas. So it warms up a lot more over high latitude northern hemisphere regions, over the polar regions and over northern Canada, over Siberia, all this area. There's a lot more warming, more than 3 degrees warming for every degree of global mean temperature warming. It doesn't warm as much over oceans. They don't warm up as much. Yeah? So the warming is very localized. So it depends where you live. You won't be getting 1.5 degrees warming with the global mean. If you're living in the middle of northern Canada here somewhere, Quebec or somewhere like that, you're going to be going up 3 degrees rather than 1 degree. Right? For every one. So if global mean goes up by 1.5, you're at 3 here, say, you'll go up by 3 times 1.5, you'll go up by 4.5 degrees if you're over the high latitude area there. So, so this is an aspect that's important. So the actual local change is not, people underestimate this thing with the number and think, oh, it's only 1.5, that sounds quite nice. Well, it won't be that nice if it goes up by 4.5 degrees. On top of that, it's very variable from year to year, and it's very patchy. So the whole world doesn't warm up 1.5 degrees each year. It'll be patchy and localized. So there's localized hotspots, and they'll go up a lot more than 1.5 degrees. So as well as this variation in the trend, there's also a sort of stochastic aspect to it where the heat wave occurs in that year. So the warming is not localized across the whole planet in one year. So you can definitely get a lot more than 1.5 degrees, even if global mean temperature's only warmed up 1.5 degrees. So that's a bit of the communication that I think sometimes is missing. And I'm going to stop there. Thank you very much for your attention. These are some penguins. They're probably okay a bit, because they live down there, so that's not too bad. If there were polar bears, it's usually the polar bear plot that people show. But anyway, thank you. That's hopefully that gives you an idea.
Okay, we now have Dario, who's going to talk about the link between global mean temperatures and disproportionate increase in extreme events.
Yeah. Okay, so hello everyone, good morning. My name is Dario. I am a postdoctoral researcher and a member of the Climate Change Task Force. So as Andrew was just mentioning, I'll be talking a little bit about this second explainer that we've done, where the aim has been to discuss and to try to get over, to the public, some simple statistical concepts that relate to extreme weather and extreme climate events. So I think just before jumping into any statistics at all, it may be helpful to just discuss what we mean, what it is meant actually by extreme weather events or extreme climate events, because the term in fact actually encompasses really very different types of events. So this picture here is actually taken from the NASA website, where they've enumerated, maybe I should say circulated, different types of extreme events. And as you can see, we have very different ones. So something that is very much in the press is heat waves. But not just heat waves on land, as we may be possibly more accustomed to hearing about, but also heat waves in the oceans, which have really devastating effects on the life in the oceans, on the flora and on the fauna inside the sea and the oceans. Well, similarly, talking about high temperatures and dry air, we may have droughts, very long periods of droughts in different parts of the world, sometimes months long, sometimes years long, according to the places you are looking at. And of course, if we're talking about dry air, high temperatures, this actually very often causes like the spread of wildfires. But on the other side, we may have almost opposite type of extreme events, which instead involve heavy precipitations or floods or entire cities being flooded by indeed heavy rain, or hurricanes, typhoons that maybe we see happening at an intensity and at a rate that even 15, 20 years ago we were not seeing. So given this spread, these different types of extreme event, do we have a way of defining simply in one way extreme events? And well, the answer is more no than yes, right? Generally, we can say that an extreme event is any type of meteorological event whose intensity is unusually large for the time and the place where it occurs. But as it is spelled out in the 6th assessment report by the IPCC, you may have more specific, more tailored definition, but they will depend, of course, upon the context. However, something that is fairly common in terms of an approach is the one to identify a specific measure according to the type of event that you're looking at. So the measure may be temperature if we are talking about heat, may be rainfall if we are talking about precipitation, and an associated threshold. And therefore, just define an event as extreme whenever the measure of that event exceeds the threshold. So in terms of actually choosing this threshold, there may be different ways of doing it. You may have just a fixed absolute value. So let's say we are talking about heat, maybe in the UK, then we simply define, we choose maybe 25 degrees as a threshold, and we say, okay, any day that exceeds 25 degrees, we are going to consider it an extremely hot day for the UK, of course. Or you may have, you may choose this threshold according to the past events. So for example, choosing it to be the 95th percentile of past observations. So essentially that value that has only been exceeded 5% of times in the past, and therefore you consider it something to be extreme, very unusual, as it is depicted here in this simple graph. Or you may define something as extreme if essentially it is a record breaker. So the threshold in this case is the maximum of all past observations, and this threshold can only, of course, increase with time. So in this explainer, we have decided to focus on one type of extreme events, which are temperature extremes, and in particular, as it was mentioned before, to try and explain and highlight some of the statistical aspects on real data coming from Heathrow Airport. And in particular, the focus has been on trying to link the relationship between a small increase in temperature and seeing how this actually affects the frequency of extreme events. So let's just have a look at this graph here. So in this graph, you may see on the x-axis we have different years from 1960 to 2023. And on the y-axis, we have essentially the distribution of maximum daily temperatures at Heathrow at each of these years. And we've divided these 64 years into two periods, each of which has 32 years. So an earlier one from 1960 to 1991, and the most recent one instead from 1992 to 2023. So just possibly by having a first look at this graph, I guess the feeling is that there is a slight increasing trend, right? So temperatures, the distribution of temperatures seems indeed to get a little bit higher, okay, to go towards higher temperature, the closer we come essentially to the present. We've decided here in this graph to just set a threshold which is 25 degrees, and therefore highlight either in blue for the first period or in red for the second, the temperatures that go beyond 25 degrees. And I also guess, hoping you are agreeing, that you can see that in the second period we have a little bit more red points than we have blue points in the first. So if we are trying then to look a little bit more in detail into this, then we've estimated, then we've just plotted here an estimate of the densities of the distribution of temperatures, the maximum daily temperatures, for each of the two periods. So again, blue is the earlier period, red is the closer to us period, the more recent period. And you can see from this graph, I mean, the shape of the distribution, a particular one is bimodal, but it's very, very similar for the two periods. The only difference is that there seems to be a slight shift to the right for the red curve, so for the recent period, than there was before. And if we want to quantify actually this shift and look at the mean, so actually the mean has gone up by 1.4 degrees. So something that possibly, you know, it may not be considered particularly big or particularly extreme. But now the question, as I was mentioning, is, okay, how does this shift actually affect the frequency of extremely hot days? And here we go into the first simple statistical aspects that we've tried to convey to the public. So when we are talking about extreme events, we are essentially talking about the tail of this distribution and essentially the mass of the tail of the distribution. So just to exemplify with a normal distribution here, really we are talking, when we talk about frequency of extreme events, we are really looking at how much mass there is beyond a given point. And the question that I was phrasing before, how does a shift in the mean affect the frequency of extreme events, is simple statistical question that says, okay, if we shift this distribution a little bit more to the right, how much is this green area going to increase? And of course the answer is that, well, quite a lot. So if we shift back and forth between these two, we're only moving the curve slightly on the right, but the area that is there increases by a lot. So if we then try to see this explicitly on the Heathrow example and on the Heathrow data, so let's see there what happens. So in this graph, on the x-axis, we have different temperature thresholds. So essentially, different ways of defining what is an extremely hot day. So for example, if we consider an extremely hot day to be a day that just goes beyond 25 degrees, then the y-axis here is going to tell us, on average, how many such days we had in a year in the first period, and how many such hot days we had in the second period. And what we find is that for 25 degrees, we have less than 19 days per year on average in the first period, but practically a full month instead of such hot days in the second period. So when we report these numbers and we compare the two, well, this means that essentially there has been a 60% increase, which is already quite impressive. But of course, this number changes according to the threshold that you consider. So if you, for example, consider 28 days, so now I'm considering a day extremely hot if it exceeds 28 degrees, then there are an average of less than 5 days per year in the first period and more than 10. So we're talking of an increase of more than 120%. So we believe it is important, you know, when you hear these figures, maybe in the news or so, it's also important to just get a little bit of understanding of where they're coming from and what really may be the true and possibly simple statistical explanations for such figures. Now I'm going to just change graph and look at a similar thing but from a slightly different perspective. So now I am fixing the temperature threshold to be 25 degrees. So I'll say for simplicity a hot day. A hot day is anything that has exceeded 25 degrees. And we are looking at, okay, how many such days we have in a year. As I said at the beginning, we have these two periods, each of which has 32 years. So, for example, we can try to see how many years had more than 10 hot days in the year. Now, in the first period, if we go up here, we find that 20 out of the 32 years, so it's also spread out here, 20 out of the 32 years had more than 10 hot days in the first period. So it's a relatively common event, a little bit more than 50%. But this event becomes, it is happening practically every year in the second period. And again, this change is this increase changes according to what threshold you consider. So if you instead want to see how many years had at least a full month, 30 days of hot days, then you find that there were 6 out of 32 years, so a fairly rare event in the first period, but 14 out of 32 years in the second one. So again, something we've gone from 6 to 14, something that has more than doubled. So what I've discussed so far is, of course, very typical of temperature extremes. So what we've seen is global warming, in terms of how it affects the distribution of temperature, causes a shift to the right, and this has a direct impact on the frequency of extreme events. But it is important to stress, okay, this is not the only thing that can happen. Climate change even climate change modeling has lots of challenges, and the ways in which global warming may affect distribution of other variables may be very different. And here we have an example. If we talk, for example, if we think of rainfall, one of the ways this has been affected is not by a change in the mean, but rather into a difference, into a change in its shape. So essentially, the width increases, the variance increases. So this means that both in the UK and in other parts of the world, we're actually having more droughts and more dry years during summer. We have more floods during winter. But overall, it's not the average that has changed much. It's another type of distributional change which relates indeed to an increased variance. As it was mentioned before, we haven't talked about this in this explainer, but it may easily be something to talk in future explainers. And we are more than happy to get your feedback and your opinions on what topics may actually be of interest, to the public. So just to then conclude, this explainer has discussed some simple statistical aspects that essentially underpin and motivate and explain the change in the frequency of extreme events. And the aim is really to aid public understanding and also provide some ground, some statistical ground for figures and data that are often had in the news, in the newspaper, and that may seem impressive, but we believe it's important to explain a little bit more where they're coming from, what they really mean. But as I said earlier, it is important to acknowledge, that connection between climate change and statistics is much more involved. There is a strong, it's much more intertwined and complex than that. There are several ways in which global warming and climate change affect distribution of variables, for example, and much more. And, we think, however, hopefully this simple example and explainer on the Heathrow data already highlights, hopefully fairly well, a simple way in which a statistical concept can be transferred that relates to things that concern climate change. So thank you very much then for your attention. This is all from me. I thought after talking so much about extreme weather, it was nice to put a nicer and very hopefully enjoyable picture of weather and the beach. So thank you very much. Any question and feedback, really more than welcome.